Greetings, everyone. Welcome into the first lesson of trigonometry. Let's get started. Of course, trigonometry should be defined as the study of something. Just like every other math can be defined the same way. Trigonometry is the study of angles and angle to straight line or linear measurements. Okay? Relationships, really. So, really what we're doing is we're going to be studying angles the whole time, but to really get the idea of why this needs to be its own subject, let's define angles first so that you can see. Okay, so an angle is not just an object. A lot of times we draw angles stationary and we picture angles between walls or between pieces of wood that we're constructing or just whatever, okay? But an angle is not a stationary object. An angle is more like an action most of the time. And what it is it's just a measure of rotation between two objects. So if I have two things that can be considered straight enough, right? And an angle is an amount that I can rotate from one object to the other object. And the reason that's important to understand is because when you have an angle and you draw an angle, like one of these, for example, the distance from this center point can get larger and larger, but the actual angle is the same no matter if I draw it small here or big over here. So it's not about distance. It's about the actual movement of one line to the other line. Okay, so an angle is really the measure of rotation between these two things. Okay, and then a full rotation would be if you could take the two objects and rotate one all the way around until it was lined back up with the first object again. Okay, what a lot of people call a circle, but you have to be careful there because a circle has an actual algebraic definition as well. So I'm going to call it a full rotation. All right. Now a degree is defined to be 1/360th of a full rotation. In other words, 360 degrees is considered to be a full rotation of measurement. So the degree is a measure of an angle. Really, it's one of our units that we use to measure angles. And it's defined such that 360 of them make up a full rotation. If you were to go a full circle from beginning to end, and what we call the initial side and the terminal side. We'll talk about that soon too. All right, and then we usually classify the size of angles into three main categories: acute, right, and obtuse. Acute angles are angles that measure less than 90 degrees. Right angles are equal to 90 degrees, and obtuse angles are greater than 90 degrees. Okay? The right angle especially is something that's going to come up quite a lot this entire lecture series in trigonometry. All of our trig is at the beginning particularly based on that right angle. Okay, a couple of other categories that come up with angles are complementary and supplementary. A lot of times we'll be interacting multiple angles, and these are two things that come up to give us some of our special relationships. Complementary is two angles who add up to a total of 90 degrees if you add their measurements. The measures of rotation of the two angles add up to a complete 90-degree angle. Okay? By the way, 90-degree angles are signified with the little square corner. If it's not there, it's not necessarily a right angle. Also supplementary, when you have two angles that add up to 180 degrees when you add their two measures. Okay? And here's some of the languages, and here's some examples of what goes along with that. I could say 37 degrees is the complement of 53 degrees. Why? Because 37 plus 53 is 90. So a 37-degree angle and a 53-degree angle are complementary. But I can also say one is the complement of the other. Also, sometimes we'll label points at the ends and in the middles of our angles with letters. And I can designate the name of an angle using the 3 points. So in this case, the obtuse angle here, ABC, and then I have an acute angle over here, CBD. And I'm saying that the measure, that's the little m, the measure of ABC plus the measure of CBD is equal to 180 degrees. And I can say that they are supplementary, and that's because the points A, B, and D are drawn collinear. In other words, they exist on the same line. It's 180 degrees because that's exactly half of a full rotation. To the two pieces, the AB piece and the BD piece, are pointing in the same line but just opposite directions. So that would be 180 degrees total between the two different sections of angle rotation there. Okay, and then something else that goes along with degrees is the DMS system, degrees, minutes, seconds system. And the reason we have this is so that we can have a higher amount of accuracy. Before we get into the examples, let's talk about the accuracy here for a second. Why exactly do we have 360 degrees in a full rotation? Where did that number 360 come from? Well, it doesn't actually have a deeply rooted mathematical reason, especially for nowadays. It's more of an aesthetics reasoning. 360 degrees is a number that's easily divisible by several things that we use. It's divisible by 2, 3, 4, 5, 6, 8, 10, 12, 15. 360 can easily be divided by a lot of these common numbers that we are going to divide by, and you still don't deal with decimal numbers. Also, 360 is a sufficiently large number that 1 degree, 1/360th of a full rotation, is still very, very small, that I can get a lot of accuracy in a rotation without having to use decimals. And back when degrees were originally invented, that was kind of important to not have to worry about fractional pieces. And even today, a lot of people like to think in terms of whole numbers. So degrees gives you that sort of comfort there. So there's a lot of things backing that. Okay? When you do actually have to start getting into decimals of degrees, we have the DMS system, which people have further invented so that they can still use counting numbers for high amounts of accuracy in a rotation. And the reason you would need something like this is possibly, for example, on a large object, like say, I don't know, the Earth. We use the DMS system. It's a degree system for the latitude and longitude measurements on the surface of the Earth. Okay? 1 degree by itself on the surface of the Earth between two latitude lines can cover around 69 miles. That's a huge gap between whole numbered degrees. So then we're kind of forced to use decimals sometimes, right? Well, that's why we have the DMS system. If you convert decimal degrees into degrees, minutes, and seconds, you can still have that decimal portion, that fractional portion of a degree, but they'll be communicated with whole numbers for the most part. So here's the system. 1 degree is 60 minutes, and 1 minute is 60 seconds. It's a lot like time, but instead of hours, it's degrees. Okay? So the same way that you would convert decimal hours, you can convert decimal degrees into our degrees, minutes, and seconds. And here's how you would do it by hand, or mostly by hand, I should say. Of course, I have 143 degrees, because that's the whole number. Plus, I have 0.835 of 1 degree, right? So if I do 0.835, and that, remember, this is a portion of a degree, times 60, right? Because 60 minutes is 1 degree, and I have 0.835 of that 1 degree. So then what I would get is the number of whole minutes with a little bit of a decimal as well, right? So you would do the 0.835 times 60, and you get 50.1. So this is what I've got. I've got 143 degrees and 50.1. And for minutes, what we do is we put this single little tick mark right here, right? The minutes can be designated with a single tick mark like this. Seconds, minutes is single, seconds is 2 tick marks like this. Okay, now look, I've got this minutes right here, but it's a decimal still. And we can go further into seconds. So here's what I do. I have 143 degrees. I've got 50 minutes, plus I have 0.1 times 60 again, because that's going to give me how many seconds, right? Because I have 60 seconds in 1 minute. So then I can give this finally as 143 degrees, and you don't need the plus signs. I can just write it out, 50 minutes, and then 0.1 times 60 is 6, right? So 6 seconds. Okay, so if you have to do those by hand, it's just, like converting time. However, also in the calculator that we use in all of my classes, there is actually a degrees, minutes, and seconds button right here. You can see it right there. And basically what this allows you to do is when you hit this, it gives you a little menu at the top, and you can go over and you see this little arrow DMS. So here's what I have to do. I can type in the 143.835 like so, and then I go into that menu and I hit to DMS like this. And then when you hit enter, you'll notice that it actually gives me the thing that we just calculated, 143 degrees, 50 minutes, and 6 seconds. Okay? And then again, in reverse, very, very similar process. But instead of multiplication, of course, we would use division. So for this one, I have 19 degrees. So it would be 19 plus, because it's 19 wholes, right? I have 21 out of 60 minutes, right? Because then that would be a whole degree. And here's where you gotta extrapolate a little bit for a second. It's 13 seconds, and I have to go 2 levels, right? I have to go 2 60s. So that's 60 times 60 here, which is 3,600. And then that will be total degrees, right? So if I do this calculation here, 19 plus 21 over 60 plus 13 over 3,600, then I will get 19.3536, and then it looks like the ones are continuous after that, degrees. So okay, again, that's if you're doing it by hand. The calculator also has the ability to do this. So here's the way I would do this in the calculator. I have my little menu with the degrees, minutes, and seconds, and what I do is I hit 19, and I put the degree marker next to it by hitting enter in the menu. Okay? Then I've got 21 minutes, so I hit the menu again, but I go over to the tick mark for minutes. And then I've got 13 seconds, and I go over to the double tick mark. And you'll notice that what I have in there is exactly the same as what I have in the original problem. And then all I do is I hit enter. And of course, when I hit enter, notice it gives me the converted piece. Okay, so you do have technology to back you up on these kind of things. And DMS is only going to come up in certain applications where a high amount of accuracy is needed in degree mode. Other times, we may not even be using degrees. We have another system also to talk about. The next thing you need to know is how we can put angles into a system that's going to relate to the rest of the graphing that you've been doing in all of your algebra and geometry classes. So what we do is we take the rectangular coordinate system, the x and y axis, and we put together the quadrant system as a rotational device. So here's what a standard angle graph is always going to look like. The standard angle always begins on the positive x-axis. You'll notice I've labeled 0 degrees there. An angle is always going to begin on that x-axis right side right there, okay, the positive x-axis. A positive angle is going to rotate counterclockwise, and a negative angle is going to rotate clockwise. So it's actually possible in this standard system to have negative angles, and it has a meaning behind it. Okay? Well, here's the way the system is set up. You've probably been introduced to the quadrants before, right? 1, 2, 3, and 4 using the Roman numerals. The whole system of the quadrants, the way they're numbered and the direction and everything, is basically to give you the idea of the rotation. And what we have to top it all off is what we call a right-handed system. To expand this later on, if you ever have to go into a higher dimension like three-dimensional graphs and things like that, we have another z-axis that comes out of the board. And if you use your right hand, you'll notice that if my thumb is that axis coming out of the center there, right? If it's a line coming out, my right hand rotates in that direction. And that's the way we've defined a positive angle, using what we call a right-handed system. It works well with all of our math and physics applications. Okay, so with this right-handed system, a positive angle is going to want to rotate in this counterclockwise direction. So then a negative angle is going to want to rotate clockwise. And I have a couple examples for you here. 210 degrees is rotated past quadrants 1 and 2 all the way into quadrant 3, right? It passed up 180 degrees. Whereas right here, negative 20 degrees just stopped in quadrant 4. And you'll notice that I have points on the end of these lines. Sometimes we actually also want to relate our angles to a point location in the grid. Okay, so we'll have this standard system to relate all of that together at one point after we're done talking through all of these beginning sections. All right, so just for some terminology, any angle, whether it's in a standard system or not, has an initial side and a terminal side. The angle is going to rotate from the initial side to the terminal side. Okay, so for a standard angle, the initial side is always that positive x-axis, and the terminal side is going to be wherever the rotation is supposed to stop. The terminal side should contain any points of interest, pun intended. It is possible to have what we call coterminal angles. Basically, the idea is two angles in standard position that terminate on the same line. They have the same terminal side. All right. Of course, they're going to have the same initial side because if they're standard angles, they're all going to start on that positive x-axis. So there's really two main ways for these coterminal angles to happen. If they're in the same direction, then what's happening is you have one angle that's more than a full rotation, possibly more than a couple or 3 or 4, whatever, right? Here's the example. If I have 135 degrees right here in quadrant 2, and then 855 degrees is also that same side, but I have to go around 2 full times. 360 plus 360 plus 135 gives me 855 degrees of rotation, right? There are some applications where you would have more than a full rotation. If we're talking about car tires, if we're talking about turning a bolt inside of a mechanism that you're building or something like that, it's possible to have an angle that rotates more than 360 degrees. Okay? And what you need to notice is they have the same terminal side. And that's going to have an effect in trigonometry that a lot of those calculations between these two angles, even though they're completely different angle measurements, they'll have very similar trigonometric calculation and results. So coterminal is an important phenomenon, right? The other way is if they're in opposite directions, then you can have, say, a positive and a negative angle, right? A positive angle and a negative angle can be coterminal. And usually what that comes from is either you're subtracting 360 from one of the angles, or if you think of it another way, if the absolute value of the two angles adds up to 360, right? 220 plus 140 being 360, then that gives me the full rotation accounted for, the entire circle, right? Accounted for. In this case, 220 rotating into quadrant 3, negative 140 rotating in the negative direction, the clockwise direction, into quadrant 3, and they terminate on the same side. Therefore, they are coterminal. Okay? If you're asked to create coterminal angles, the way to do that is to either add cycles or subtract them. That's typically the easiest way to do it. So if they hand you an angle, either add 360 degrees or subtract 360, or if you're in another system, add full cycles or subtract full cycles, full rotations from the angle in question. Next, we need to talk about another measurement system for angles. Degrees is great, and it's probably the first one you learned, and it may very well be the only one you've seen, and maybe you've seen radians before. The point is, radians is an important measurement system because it has something that degrees does not, and it's a very important thing, and that is a natural connection to what an angle actually is created from, and that's rotation. Okay, so degrees is just a generic system that was made to fit a certain mentality, and it works great, especially when we're just communicating everyday things. But radians is a infinitely useful system and becomes pretty much the main system of use once you get to calculus, because of the natural connection that this is made from. Okay, so here's what a radian is. A radian is the amount of rotation that it would take for someone walking in a circular path, okay, while they're walking, while they're tracing out this circle as they walk, for them to walk a distance that's equal to the radius of the circle that they're walking on. So let's go through that again. 1 radian is equal to however much rotation it takes to walk a radius length on the edge of the circle, on the circle itself, that radius is measured from. Okay? With this particular circle that I've drawn, it actually has a radius of about 3 inches. Okay? So the way this is mapped out right here, 1 radian has a distance of 3 inches along the edge of the circle there. So if I were to take that little arc, that piece of the circle, straighten it, measure it, it would measure around 3 inches, right? Okay, so that's 1 radian. Notice I can do that a few more times, right? And then I've got a little bit left over. And it's supposed to be that way, okay? The circumference of a circle is 2 times pi times the radius. Now 2 pi, just the number itself, is 6.28. 2 times 3.14, around 6.28. Notice 1, 2, 3, 4, 5, 6, and then there's your 0.28 for the circumference of the whole circle. So this system is actually based on the fact that every circle has a circumference based off of its radius length. So 1 radius length gives me 1 radian of rotation out of a full rotation. Okay? And what that ends up being is around 57-ish degrees. It's a little bit more. It's got a decimal after it, but it's around 57-ish degrees. Okay, but again, notice, right, that there's 6 of these all the way around the edge. I did the complete circumference. And then this is going to be 0.28-ish times 3 inches. That's going to be the length right there. Okay, so the main thing to remember is that a radian is based off of the radius of the circle. So, oh, well, Professor Simon, does that mean that if you have a smaller circle, a radian is a smaller amount of rotation? Or if you have a larger radius, is it a larger amount of rotation? No. If I have a larger circle, let's say, and forgive my free-handed yuckiness here, okay, but imagine if I have a larger circle here, and then I just continue this radian out right here, right? Notice the radius is bigger, but then so is the arc that I'm sweeping out right here. This radius is roughly the same as that length right there. So it's the same amount of rotation because of this connection to circumference. There is a natural connection of a radian to what an angle actually is. It's the amount of rotation, and it's a piece of a circle that will always be that same relative size, right? The radius gets bigger, but then so does the arc. So the amount of rotation it takes to make that radius happen on the circle always remains the same. And you will always have 2 pi radians in a complete rotation because 2 pi times a radius is the circumference, 1 full loop of a physical circle. So a radian is a measurement system that's actually connected to the physical being of a circle itself, a perfect, shape for rotation. Okay, so 2 pi radians is a full rotation. Well, that means that 2 pi radians is the same as 360 degrees. And now we can convert because we have the 2 things that are equal. Typically, we think of it as pi radians and 180 degrees just because the numbers are smaller for half circles, right? But it doesn't really matter. It's still the same conversion. Here's another thing. Radians is considered sort of like the default angle measurement, especially for a lot of your advanced mathematics. So what happens is we don't even bother writing the RAD, okay? For many reasons, not just being the default. Radians is what they call a unitless measure because of one of the things I'm going to show you in a minute dealing with the length of an arc of a circle. Radians actually can exist just as like a free-floating number, a multiplier, if you will. So radians, you don't actually have to write a unit afterwards. I actually don't have to write the RAD. But if it doesn't have a unit after it, like the RAD or something like that, it's automatically radians. It has to have the little degree circle for it to be degrees. If you see an angle and there's no little circle for degrees, it's automatically radians. Okay, keep that in your mind. Highlight that, write it down, whatever. Make sure that you never forget the degree marker if you want to discuss degrees, like say on a test or whatever, because that could get marked wrong, whoever's grading your test and stuff. Okay, so let's do some conversions here. I want to convert 128 degrees into radians. Okay, so the way I would do that is I would take the 128 degrees and I would multiply that times pi over 180 degrees. And this is sort of, what I was always favorably called the chemistry method of conversion, right? Where you put 2 things that are equal in a conversion on top and bottom of a fraction and then multiply across. And the visual effect, it isn't actually what's happening, but a lot of times people will use the visual effect of crossing out the units to make it fit. So notice I have a degree in the top, so if I have a degree in the bottom, it's all lined up correctly. Okay, so in my calculator though, what I'm going to do is I'm going to punch up 128 times pi divided by 180. And of course, pi being an irrational number, you really do need a calculator for this. So 2.234 radians ish, right? 2.234 radians. Now again, I'm going to put the RAD just because for context. But I don't actually have to write the RAD because we're in the understanding that this is an angle measurement and radians would be the thing that you would assume it is if nothing is written there. 45 degrees. Okay? Now there are some special angles out there. 45 is one of them. And when we convert those special angles, we leave it in what we like to call the exact form. So 45 degrees, if I do the conversion, I would take the 45 degrees and I would multiply by the pi over 180 degrees. But notice I can reduce 45 and 180 because 45 degrees is exactly half of a quadrant. So 2 45s is 90 and then 2 90s is 180. So 45 is actually a quarter of 180. And so I can reduce this to pi over 4. The degrees goes away because I'm converting into radians, right? So I can actually say that 45 degrees is equal to pi over 4 radians. And again, I don't have to put the RAD, but I'm using it for context. All right, other way around. Let's convert some radian measurements, right? Notice no little circles, no anything else. Those are radian measurements. Let's convert them into degrees, right? Okay, so to convert 1 radian into degrees, I would take the 1 and I'm going to multiply by 180 degrees over pi. Notice it's exactly the reciprocal, again, because I have radians at top, so I should have radians in the bottom. And then what do we get from that? 180 divided by pi, 57.295. So we'll just use 57.3. degrees. All right, next, 8 pi over 3. That's one of the ones that's in that exact form, right? So I would do the 8 pi over 3 times 180 degrees over pi. And since it's in exact form, I can go ahead and say pi divided by pi is 1, right? So those end up going away. And I can do 3 into 180, which is 60, and then times 8. So I get 480 degrees. 8 pi over 3 radians is equal to 480 degrees. All right? Here's something that comes directly off of the definition of radians. And here goes radians flaunting that natural connection that degrees will never have. This is something that degrees just simply can't do for us, that radians naturally just gives us by being defined, by existing. Okay? The length of an arc of a circle as related to an amount of rotation. Okay? So notice the way I've defined radians, right, uses the radius of the circle, which also is linked to the circumference of the circle. And therefore, let's say I have the radius of 3 inches for this circle like I did before, and I want to rotate 3 radians. How much distance is being traced along the edge of that circle? In other words, what arc length of an arc is being traced out? Well, each radian gives me a radius length, right? This will be 3 inches, this will be 3 inches, and this will also be 3 inches, right? So then if I've got 3 radians with 3 inches each in arc length, then I would have a total of 3 radians times 3 inches. And arc length is designated with the letter S for a total of 9 inches of arc length. And notice that's exactly the formula that we have here. The length of the arc is going to be the angle times the radius. But, and this is a big but, make sure you see it, this theta must be in radians. Radians only. Okay? So I can actually take an angle, if it's in radians, multiply it by a radius, and I'll get a piece of the circle, an exact measurement, if I were to straighten it and measure it with a tape measure, a ruler, whatever. Okay, if I could actually lift up that piece of the circle and straighten it out. But I don't have to now, because I can calculate it. Also though, more importantly, this also gives me a way to create radian angle measurements. Now, I want you to think about this for a second, especially in all of your previous math classes. If you were asked to measure an angle, you had to pick up one of these if you wanted to be really accurate, right? You had to say, let me just line this up. What I'm talking about here now is, well, how do we make these? Or how do I create some sort of angle that's accurate in measurement here so that I can know exactly what that is? Well, this is it right here. Radians has this natural connection not only to the radius, but to a length on the outer edge. If I want to know what this angle is right here, such that the radius of this circle is 7 feet, and it happens to map out an arc of 26 feet when you unfold the angle, when you actually let this piece rotate to here, right? Initial side to terminal side. It maps out 26 feet on the edge of the circle there, and the radius is 7 feet. Well, my arc length formula gives me a direct relationship there of 26 feet is equal to the angle theta times the 7-foot radius. But I can solve for theta, right? I just divide both sides by 7 feet. And notice the feet are gone. That's going to always happen because the radius and the arc length should be measured in the same units. They have to be. So then what I get is 26/7 is my theta, my angle. This is my angle in radians. My angle in radians is 26/7. And that's an actual angle measurement. Notice it's unitless, like I mentioned before. Radians are unitless. They're like multipliers. Okay? It's an amount of something. It's a portion of a rotation. And therefore, it by itself can just stand alone, unitless. Right? Now, let's convert that real quick into degrees by doing 26/7 times 180 divided by pi. And I get 212.8 degrees. Notice that makes sense. It's a little bit past halfway here, right? It's in the third quadrant, if you will. If this were the x-axis over here, that is past halfway. It's past 180 degrees. It looks about right. It should look about right. Okay? If those are the true measurements. So if you're just out there and you have, this circular thing, or if you're trying to measure some angle, what you need to do is just find an arc, something that you can easily put a tape measure around, and then find a radius, again with the tape measure, and then you can quickly calculate an angle in radians just by dividing the two. And then if you really need it in degrees, you can convert it like we just did. Okay? So radians is this natural connection to rotation. Here's an example right here. Two pulleys are connected by a belt, right? or if you want a bike chain, or just whatever you can imagine two gears or two pulleys are connected with, such that when one turns, it causes the other one to turn as well. Okay, and we're also going to assume that there's no slip of the belt or the chain or whatever it is that's connecting the two pulleys or gears or whatever it happens to be. Okay, so what that means is you have a 1-for-1 exchange of length of rotation. In other words, arc length. So as one of these things turns, the length that the belt moves is going to be equal between the two of them. Because when one of them turns, the belt moves by some length. It has to do that all the way around to stay evenly distributed like it's supposed to, right? So you have that same length moving around the other pulley. Except I say that the angle of the big pulley turning is 35 degrees. Okay? What kind of angle is that going to cause the small one to turn, since turning the big one will turn the small one, right? Well, the arc lengths have to be equal. In other words, the radius of 2, right, 2 centimeters, times whatever angle we're missing, we'll call it theta, right? That's an arc length, angle times a radius, has to be equal to, and we'll call it arc length of the small, right? Has to be equal to the arc length of the big one. Arc length large. Which is going to be 5 centimeters times, now wait, be careful. Remember, arc lengths only use radian angles. If I put 35 degrees here, right? If I put 35 degrees there, I'm not actually calculating an arc length. Okay? So be careful. So right here, I'm going to have 35 times pi over 180. I'll go ahead and just convert it in one big statement, right? All right. So then right here, if I divide both sides by the 2 centimeters, notice the centimeters go away here like they're supposed to, and I would be left with my angle measurement, whatever it happens to be. So theta is approximately what? Let's go ahead and punch this up. I have 5 times 35 times pi divided by 180 divided by 2. 5 times 35 times pi is the top, okay? Now I'm going to do divided by the 180 and the 2. So I get 1.527 radians. Okay, now notice I just didn't put anything there, right? Well, Mr. Simon, they gave it to us in degrees. What if we need to communicate it back in degrees? Well, it's in radians. Convert it back to degrees, right? I'll do this number, the 1.527, okay? I'll do times 180 divided by pi. And I get 87.5 degrees. So I've got both of them at my disposal. And I know what you're thinking. Well, couldn't we have just wiped this out since I undid it with this? Coincidentally, yes. But in all of your situations, you can't just look for easy ways out. Okay? Use the actual definitions on these things. Make sure that you make sense of what's going on. In this case, arc length equals arc length. So I know this is a radian measurement and this is a radian measurement, and I've got everything where it's supposed to be. Keeping track of everything so I don't lose track with all of these small little shortcuts. Something else that comes along with the definition of radians is the area of a sector of a circle. A sector of a circle is just when you take 2 radii and basically take a slice out of the circle, like so. So if I'm calculating the area of a sector, then what I'm doing is I'm calculating the amount of surface that's inside of the 2 radii and the arc. Okay, now this isn't a normal area that you would have done in just plain old geometry. This is something that has a curved side and two straight sides. So it doesn't actually, fall into one of those old formulas of triangles or whatever. Okay, so then how do I find the area of the sector? The way you should think of a circle now is the perfect symmetric object. Okay, a circle is basically the area. I mean, if you want to fill in the whole space, just think of it like stacking radii over and over and over and over and over and over again. Right? You keep stacking the radii lengths. Okay, and it basically fills up the whole circle. Well, a sector is just some of those radii stacked. In other words, it's a portion. But the way circles are perfectly symmetric, you can do a proportion or just do portion sizing, like the way you understand percentages and decimals to be portions of something. Okay? For example, the area of a circle is pi times the radius squared, pi r squared. The portion that we're interested in is the angle theta out of a possible 2 pi radians. Okay, now notice I've put theta in radians, okay? And this is the portion of the circle. The circle is perfectly symmetric. So this portion right here accurately represents the portion of the area also that we happen to be interested in. So if I'm interested in this piece of this area, then it's just a multiplication, right? This portion of this object, right? Of me giving us the multiplication here. So the pi and the pi right here, pi over pi is 1, those wipe out. I'm left with a 1/2 because of the 2 in the denominator. I have theta and I have r squared. And that's the area of the sector of a circle, 1/2 theta r squared. And again, the theta has to be in radians for this to work. Okay, so here's an example of it in use. Calculate the volume of a deep dish pizza slice. And yes, I am a huge nerd, and this did actually occur to me at a birthday party for one of my children that this would be a cool problem. Okay, so the volume of a pizza slice that's deep dish, right? So it's an inch thick, big old deep dish with thickness of 1 inch. Side length on the side of the pizza slice is 8 inches, and the crust, in other words, the arc of the circle of the pizza crust, right, is a 5-inch length. So we're going to find the volume. Well, volume is really just an extension of area, okay? So what I'm going to do is I'm going to find the area of this sector of the pizza and then just multiply by the thickness. That's it. Okay, so here we go. First off, to do the area of this sector, I need an angle, right? I need an angle. Also, it would be extremely helpful if that angle was in radians. Well, guess what? We just talked about if I have an arc length and a radius, because remember, the side of a piece of pizza is technically a radius if it's cut right? The rest of the pizza is going to be like this, and you're just doing a sector of it. The 8 inches is the radius of the pizza, 5 is the arc length. So I can easily calculate theta as just 5/8, 5 inches divided by 8 inches, right? The arc length divided by the radius. That was from the last example that we talked about. I can find an angle in radians very quickly if I know an arc length and a radius. Okay? So then what's the area of that sector, right? The area in here. This area in here is going to be 1/2 times 5/8 times the radius, which is 8 squared. Also notice the units here, right? The units of the angle is nothing. Remember, it's unitless. And then I have inches squared, which is what an area should be. Okay, so then what about the volume? The volume is going to be that area calculation times 1 inch thickness, right? Because it's just times the height, basically. All right, so let's do this calculation, and notice this is inches here, and this is inches being squared here. This is unitless, and that's just a half. So notice I'm going to get cubic inches for my volume unit, right? So my volume is going to be equal to 20 cubic inches, because I have 5 times 8, which is 40, and one of the 8s, because this is 8 squared, that's technically 2 8s, one of them wipes out with this 8 in this division, so that's why I just have 5 times 8 times a half times 1 cubic inches of volume there. Okay? One more generic application of angles here. I'm going to take a little physics spin on this. Linear speed related to angular speed. Okay, so angular speed is just how fast something is rotating, how fast the measurement is changing on an angle, basically, okay? And we have a relationship, we have a way of connecting an angle to an amount of distance, as long as that distance can be related to the edge of a circle somehow, okay? So that's this, the arc length. The arc length is the angle times the radius of the circle. But if I were able to take that length and divide it by time, you've done this before, anytime you measure the speed of something moving forward, right? Oh, I was traveling at 10 miles per hour, right? Distance divided by time, miles per hour, okay? Distance divided by time is just speed. So that's what I'm doing on the left side here. I'm labeling it with V because a lot of times velocity is the word used. Speed is technically what we're doing right now though. Okay? But if I divide by time on one side, of course, to keep it balanced, I have to divide by time on the other. It would not make sense to divide by time with the radius of the circle because we're assuming that the circle is not increasing or decreasing in size. The radius is constant. It's not going to change over time. Okay? So what I do end up doing those is dividing the angle by time. So that right there, the angle divided by the time gives me what we call the angular speed. Okay? Rotations per second, radians per second, revolutions per minute, RPMs, you probably have heard that a lot, right? If you're oldie like me, RPMs even had to do with record players, right? And how fast are you turning the record player because they have different speeds, okay? Or okay, for more modern people, how fast is the DVD spinning in the player, right? Okay, so angular speed is just some sort of angular measurement, usually either rotations, revolutions, or radians, something like that, over time. But since length is, compared to an angle, then linear speed, straight speed, is the same relationship with angular speed as long as they're coming from the same phenomena, from the same object. For example, a tire or a wheel or some sort of gear rotating on the ground, right? If I let the wheel rotate this way, right, the way that I have the arrow pointing, then this length would be the length that it peeled up off the ground, okay? And so this straight distance that the wheel has traveled is related to the arc on the edge of the circle, which of course is related to the amount of angle that the wheel had to turn for that length to be traveled. Okay? So you have the same relationship where the angular measurement is just multiplied by a radius to give me the straight line measurement. Okay? So a good example is a vehicle. Okay? Maybe you know this, maybe you don't, but a vehicle measures the speed in which you are traveling by clocking how fast your wheels are turning. And by the way, if you change the radius of your tire, you have to change the calculation in the computer for your speedometer, or else you will not have an accurate measurement of one of these. Okay, so if you increase to, say, the 44-inch big, mud riders that you like to put on your rising truck or whatever, make sure that you increase the calculation in the computer, or else you could be traveling what you think is 70 miles an hour and you might actually be doing closer to 100 on the interstate, because the radius being bigger means that each rotation would cover more distance, right? That's this relationship right here. So example, a car traveling forward with 11-inch radius wheels that are rotating at 14 rotations per second, 14 full rotations every second. How fast in miles per hour is the car traveling forward? Because of course the car is connected to the wheel and the wheel is traveling forward, so hopefully the car and the wheel are the same speed, or else this is a much more interesting problem of a crazy accident or something. Okay? So let's start with, what's the omega? That's what this letter is, by the way. I know it looks like a W, but it's actually curvy. The omega here, the angular speed, let's calculate what that is. In radians though, because this for this calculation to work, this angular speed right here needs to be in radians, like all of the other ones we've been doing. Okay, so I have 14 rotations, full rotations every second. So what's my angular speed here? I've got the 14 rotations, right? But that's in rotations per second. Okay, that's not what we need. Instead, I'm going to look at it like this. A rotation, one full rotation, is 2 pi radians. Right? So in other words, one rotation here, this guy right here, became 2 pi radians. Right? Okay. So my angular speed, my angular speed is actually going to be equal to 28 pi radians per second. Okay, that's the angular speed of the tire, the wheel. If you had a point on the edge, right, you'd be able to convert that to what we're about to calculate here. So my linear speed, V, is going to be that 28 pi radians per second times the radius, 11 inches. So now notice what I have is something that's going to be measured in inches over seconds. In other words, inches per second. And that's a straight velocity, inches per second. The only caveat here is that the question actually asks for miles per hour, because of course, most of us like to be able to read our speedometer quickly. Okay, so I just need to do a few more conversions. Let's do this the chemistry way, right? That's the funny name that we always use for it. Do the top and bottom of the fractions, right? So I have 28 pi times 11, and that's inches, and in the bottom I have 1 second. So then to convert it into miles per hour, I just need to convert the inches to miles and the seconds to hours, right? Well, let's do the seconds first. There are 3,600 seconds in 1 hour, right? So now my seconds are gone, and there are, wait for it, in 1 mile, there are 63,360 inches. It's a palindrome number. It always sticks to me really well. It's a really cool number. The inches are, of course, going to go away now, and I'm left with miles over hours, or in other words, miles per hour. So in my calculator, I'm going to punch up 28 times pi times 11 times 3,600, and then divide by 63,360. Okay, so 28 pi times 11 times 3600, and then divide by 63,360. I'm getting 54.97, or approximately 55 miles per hour. Okay? So I hope that this has helped you get an introduction to angles, the way we measure them, the way we categorize them, the way we standardize them. Next, we start talking about the actual trigonometric connections that allow us to take angle measurements and relate them to even more straight line and linear measurements.